So when the abstract for this was submitted, Fernanda submitted it as PI. She's recently had a life change, and as a result, she told me that I had to give the talk. And as a result, I'm sure you're going to hear a poorer quality product. Forgive me. Here's the outline. So I'll give a brief discussion of Summit's architecture from a machine learning perspective. Many of you were in the room for the previous talk, so I won't belabor the points. But then I'll jump into some preliminary results on Summit from the Coral 2 deep learning suite relative to the Titan performance. I mentioned already something about the Coral procurement process. We are starting it again to build the machines that will replace Summit and Sierra, for example. It's known as Coral 2. And there is a deep learning benchmark suite associated with that procurement, and that's what's been used for the work here. And then I'll go through some number of these 4 case studies in terms of applications of deep learning in terms of science that have emerged these recent years, really over the last couple of years, in health data analytics, high energy physics, plasma physics, and materials. And I'll conclude this section just by saying a little bit more in detail about how we're going to execute our project called Frontier that will replace Summit. So indeed, coming in 2018, Summit will replace Titan. Summit is slated to be more powerful than any other existing supercomputer. Let's see what happens later this year. This is the architecture. Power 9 nodes and NVIDIA Voltas integrated into the node. And there are 18 of these servers per rack and 256 racks. So altogether, there are 4,608 nodes, 27,000 plus NVIDIA Volta GPUs, and 9,000 Power 9s. So Summit's expected to be a smart supercomputer. Some have said this, some in the leadership at our laboratory, smart supercomputer for open science. So, but what makes a supercomputer smart? In trying to answer this from an architectural point of view, it's GPU brawn. Summit is linking more than 27,000 NVIDIA Voltas. It's a very large number by any scale in terms of the extent to which deep learning frameworks have been scaled out. Today's state-of-the-art results are in a few thousand GPUs. There's an opportunity to do 10x more than that over the next few years. There's a high-speed data movement that's at least ameliorating the bottleneck between the CPU and the GPU, and actually GPU direct type communication. The NVLink high bandwidth technology that's built into the Summit architecture is responsible for this in a significant way. And then memory where it matters. So the new levels of memory hierarchy associated with the high bandwidth memory, the DDR4, and the NVRAM provides opportunity for data staging and for, as a result, better data performance scaling. Here's the node architecture again, showing the 2 Power 9s and the 6 GPUs on each node. 300 gigabytes per second of NVLink shared on each side of the node architecture. When we start thinking about data analytics and learning, the early results show what one would expect is that the deep learning codes like the convolutional neural networks, or for example, ResNet 50, really excel with performance on the GPUs, and the NVRAM memory is really helping with the scaling. That's what we're seeing in the early days. The more traditional data analytics like principal component analysis, k-means, so far they've been implemented on the CPU-only version of the architecture, and that seems to be also performing very well. So here I'm going to again reference Coral 2 benchmark suite. These are available online. There is one for big data analytics. which has PCA, k-means, support vector machines, all implemented through a framework called PBDR. I'll say a word about that in a moment. And then there's a deep learning suite, which is composed of a CANDLE, which is a partnership between DOE and the National Cancer Institute to build deep learning frameworks, and then also CNN and ORNN and ResNet 50. All these codes are available on the website that's listed at the bottom of this slide. So what is Coral? Coral was created by DOE as a collaboration between Argonne, Oak Ridge, and Livermore to procure pre-exascale systems like Summit, Sierra, and exascale systems like our Frontier in the future. And so in doing so, align the strategy and resources across the DOE enterprise. Coral gave us Summit and Sierra, respectively, at Oak Ridge and Livermore. And our labs are again working to deliver another RFP, and the details of that are contained here, including these benchmark suites that are going to be referenced. There is something called PBDR that was produced at the Oak Ridge National Laboratory and the University of Tennessee, primarily by George Osterkoff. It is an implementation of the R statistical package framework that has HPC libraries on the back end that enables R to run at scale in an HPC environment. And this is one of the products that's leveraged in the benchmarks. And I just wanted to highlight this in case you weren't familiar with it. This works very well. So here's some of the preliminary results. For deep learning codes running on small numbers of nodes, comparing Summit Dev and Summit. Summit Dev is our early access development system based on Minsky nodes, that is the Power 8 processor with NVIDIA Pascal. The CANDLE code is the one resulting from the National Cancer Institute DOE partnership. The convolutional neural network benchmark codes are more memory intensive, so you're seeing more of a speed up there. These are speedups measured relative to the same codes running on Titan compared to Summit. Now, I will say that these runs are being performed just as the benchmark codes have been downloaded. There hasn't been any optimization. So this is just downloading the code and running it, and what we're seeing on small number of nodes. ResNet 50 has been scaled out to 64 nodes or 384 GPUs on Summit, and this is the strong scaling plot shown here. In terms of the big data analytics, Speedups, these are the kinds of results we're getting on 1 node, 2 node, and 4 nodes. There's weak scaling data for these analytics and also some strong scaling data. The basic story here is the code implemented through PBDR does a weak and strong scale. Shifting a little bit, so if Summit will be a very smart supercomputer, but what can a smart supercomputer do for science? There are 4 topics here that have been emerging. There are many others, but I've selected these. Next generation materials, fusion energy sciences, high energy physics, and combating cancer. So just as a first example, zeroing in on text understanding in an automated cancer report classification. The opportunity here is to try to read cancer pathology reports and extract valuable information. The challenge is that there's a massive number of these reports, and they're full of errors, and they're managed in distributed databases in the United States within each state. So if you want to pull together a large database of cancer pathology reports and read them in order to gain important inferences, it's a huge task. Certainly heretofore, more than that could be done in the context of a human-based analysis. Gina Taurasi at Oak Ridge and her collaborators are building hierarchical attention networks, or HANs, as a way of training and extracting data from these cancer pathology reports. The bottom line here, as their first test case, they were able to to analyze 2,500 cancer pathology reports and correctly predict the key information like the type of breast cancer that was described in the cancer pathology reports and other key pathology information. So in this chart, they're showing in the blue key words that are identified in terms of learning, or key phrases in the red. A very different field comes in terms of high energy physics, where the Titan supercomputer has been used to develop an evolutionary algorithm capable of classifying events in high energy physics detectors. In this case, they are neutrino events in an experiment at Fermi National Accelerator Facility. This is a classic problem in high energy physics, is to identify the vertex that indicates that a reaction occurred and then classify that vertex. This is being done at Fermilab by themselves, but with Titan they knew we had a large GPU accelerated cluster, so they wanted to do better. The team at Oak Ridge, with whom they were collaborating, had a framework for enabling the genetic algorithms to improve the architecture, to improve the way the deep learning network was put together. And indeed, they were able to significantly improve the performance of Fermilab's classification algorithms. This evolutionary neural network has a name. It's called MENNDL, and it's been applied to a variety of data sets in addition to high energy physics, standard computer vision data sets, and small angle scattering experiments at the spallation neutron source at Oak Ridge. So this is one way to scale up and use a large resource. This is very expensive, of course, because it can leverage a very expensive machine for training, but it can do the job. And it gives insight in the fact that when one is presented with a data set, one doesn't know from the beginning what architecture to use for the deep learning neural network. And so how do you construct the hyperparameters of this network? What choices should you make? I imagine that in the future we'll learn much about these kinds of questions. Right now we don't know, no one can say, but we do have these kinds of proof of concepts that you can improve the network, you can improve the performances through optimization techniques like genetic search. Bill Tang at Princeton Plasma Physics Laboratory has been pioneering an approach in fusion energy sciences that's novel with respect to plasma disruptions. A plasma disruption in a tokamak is a bad event. You can think of it as a heart attack for the tokamak, in which the energy would be dissipated from the plasma and it may find itself impinging on the wall in such a vigorous way that it could damage the reactor. These kinds of disruptions are more serious as the scale of the reactor increases, like the ITER reactor that's being constructed in France right now by a multinational team. It's hard to imagine that we will ever be able to simulate the complexity of these events using first principles theory-based approaches, because we need to know that a plasma disruption is going to occur within tens of I can't remember, is it microseconds or milliseconds? I can't remember. It's very fast, right? Milliseconds, okay, tens of milliseconds, thank you. And so the idea here that Bill hit on was that JET, the Joint European Torus, had a large trove of data that was available from a multi-year experimental examination of these events. He got access to that data and began training neural networks to identify these disruptions in a very timely way. And it's, another key notion here is to be able to train the network on one reactor, for example, JET or one of the domestic tokamak reactors, and then apply it to another reactor like ITER, because we probably won't be able to take the risk to train neural networks from the beginning using data from ITER, because the risk may be very high. So he's using TensorFlow plus MPI plus other approaches that I probably don't have a report of, but he's been able to scale out on several large GPU-accelerated clusters like Titan in Oak Ridge, Pittsdijnt in Switzerland, and also Tsubame 3 in Tokyo. So time is moving on, so I think I'm going to jump over the materials example and just say, again, Summit is still under construction. We expect that the machine will be accepted later this summer. Users are getting on now, and we'll continue to enable them to get on. We're continuing to work on the node and file storage installation and the software testing. I would like to say one word about our plans to replace Summit. We're currently operating Titan, and we will continue to operate Titan until September of 2019. That's a long time for a supercomputer. So Titan was installed in 2012, and we're telling our users that we're going to operate it through 2019. We will overlap Titan and Summit by something like a year. We will, as I said, we'll begin running on Summit. We're running on the part that we have available now, but we'll accept it later this summer and put it into full user operations in calendar year 19. We've been preparing our call for proposals for Frontier, the machine that will replace Summit. We've been doing this for several months. We almost have approval from DOE to finalize this process and go into a new procurement opportunity for Coral 2. If things stay on schedule, we very much could be announcing the new partnership for the Coral 2 machines around the end of the calendar year, the current calendar year. We will do all the things we've done before. We'll do application readiness. We'll prepare our applications. We'll prepare the facility. And the idea is that the installation process would begin in 2021 for Frontier, and in 2022, we'd begin operations. And then we would have some period where Summit and Frontier are available at the same time as we transition to full operations. Importantly, from the beginning, very much like the Aurora project at Argonne, in addition to advanced simulations, now data analytics and artificial intelligence approaches are fully being considered in the design and the request for proposals from the beginning. So all these missions need to fit together in our compute and data infrastructure. And with that, I'll conclude.